Hi everyone, here are your notes for section 4.4. So now we're really going to get into the fun part of trigonometry that we deal with in pre-calculus, which gets us into the unit circle. So we use the unit circle when we're dealing with exploring trigonometric functions. The unit circle that we will develop is the most useful tool in trig. It provides an easy way to know and recall trig values of the most popular angles. So to be successful in this class and then later in calculus and beyond, you must understand it and you must memorize it. We will have a quiz that is just solely specific to the unit circle, so you want to make sure that you got your unit circle down. In order to have your unit circle down, you need to first remember your relationships with our special right triangles. You need to get these facts ingrained in your head on the 30, 60, 90 triangle and the 45, 45, 90. So let's first go ahead and focus on the 30, 60, 90 triangle. So if you remember from when we did our right triangle trig, the ratios of our sides, if my short leg was x, then the long leg was x square root 3, and then the hypotenuse is double your x. So let's go ahead and tweak that a little bit so that my hypotenuse is actually 1. Right? So if we remember back when my legs, ignore this for a second, don't write this, just watch. When this was 1, we doubled that to get to our hypotenuse. So if my hypotenuse was 1, then my short leg would be half of that, so 1/2. And then what's the relationship from short leg to long leg? We multiply our short leg by a square root of 3, right? So my long leg here would be 1/2 times the square root of 3, which would just be square root of 3 over 2 in its simplified form. Okay. You really want to make sure you have that, because when we get into the unit circle, we're going to have a hypotenuse of 1. So you want to remember that the short leg is 1/2 and the long leg is root 3 over 2. That's just something you need to get stuck in your head. 45, 45, 90 is a bit easier, because if you remember, our relationship was that the legs are congruent and the hypotenuse was x times the square root of 2. So don't write this, just watch. If my legs were 1, then this was 1 times the square root of 2, or just square root of 2. So now let's make the hypotenuse 1. So to go from here to here, we multiplied by the square root of 2. So to go backwards, so to go from here to here, instead of multiplying, we're going to divide by a square root of 2. And 1 divided by the square root of 2 rationalized is root 2 over 2, right? So my leg, if the hypotenuse is 1, is going to be root 2 over 2. And since it's an isosceles right triangle, both legs are going to be congruent at root 2 over 2. Okay, so these are some things that you need to have memorized. 30, 60, 90, and 45, 45, 90 triangles, because that's going to make your life much easier when you have to memorize the unit circle. Okay, so now let's go ahead and start talking about the unit circle. The unit circle is a circle of a radius that has a radius of 1 that's centered around the origin. So there's a diagram of a unit circle. We have theta in there as the central angle. We have point P being represented as some point on the circle. My radius is 1. So if you guys remember, your equation for a circle is, well, it was, or is, x minus h squared. Remember seeing this? Y minus k squared equals r squared. But since the origin is at 0, 0, your h and k goes away. So it's just x squared plus y squared equals r squared. Okay. So that's our unit circle. Okay, so now I'm going to deviate away from your notes for a second, just kind of do a bit of a demonstration. Okay, so you can either throw this in your notes or just watch. So if we talk about a circle on a coordinate plane with its center at the origin and a radius of 1 all the way around, oh goodness, let's see how good of a job I make making a circle. That wasn't terrible. I know that the coordinates of this point right here would be 1, 0. The coordinates on the left side would be -1, 0. My coordinates on the top would be 0, 1, right? And my coordinates on the bottom would be 0, -1, right? And then inside of that circle, if you guys remember our video, there's triangles everywhere. We can create a right triangle, right? So if I know that this is my radius here of 1, then if I make a radius, let's say here, out to point P, that would also have a radius of 1. Right? Do you see that? So now let's think about this as an actual angle. So let's call this theta. If I drop down a perpendicular line to that x-axis, I now created a right triangle. Alright, so I'm going to call P as x, y. So now let's think about what the dimensions of this triangle would be. Well, what would be the length of that horizontal leg, I guess we want, or the adjacent leg, if we want to think about it in our right triangle trig? Well, it would be representative of whatever this x would be, right? Wouldn't it? So this would have a length of x. Oops, I'm in highlighting mode. Oop, there we go. And then if we wanted to think about the length of the opposite leg, well, wouldn't that just be whatever my y coordinate would be, right? Because wouldn't that match up with y over here? So let's go ahead and label that as y. Right, so now do you see how there's all sorts of different ratios happening? So if I think about that right triangle in the inside there, okay, what would be the cosine of theta? Well, remember, cosine of theta is adjacent over hypotenuse, so x over 1, or just your x. Your sine of theta, so sine is opposite, so y over 1, which would just be y. So really, we can think about this point in terms as cosine theta, comma, sine theta, instead of just x, comma, y. Okay, so your cosine of your angle would be whatever that x value is. And then your sine theta of that angle would be whatever that value is at that angle. So when we throw in specifics, let's see if I can delete theta. Oh, too big. Let me just have that in there. So let's say we threw in a 45, 45, 90 degree triangle there with a hypotenuse of 1. My new x value now, we just said, was what? Root 2 over 2. And our new y value is root 2 over 2. So the cosine of 45 degrees would be my x, root 2 over 2. Or my sine of 45, now this is when your r is 1, this only works when your r is 1, right, would be my y, which is root 2 over 2. See how that works? Because technically it's over 1, so it wouldn't go away. So if my radius was larger, it wasn't at 1, then it would be root 2 over 2 over, let's say, the radius of 3. And then you would go from there. Okay, or if I made everything, let's make it a 30, 60, 90 triangle. There we go. Almost. There we go. So I'll put, let's make 30 degrees here. Okay, so if we remember what would my short leg be on a 30, 60, 90, well, it's half of the hypotenuse, so my y would be 1/2. My x would be multiplying that by a square root of 3, so square root of 3 over 2. So now my cosine of 30 degrees, which remember is the same as your cosine of 30 divided by 180, so pi over 6. Same thing, just degrees radians, would be equal to my x, which is square root of 3 over 2. And then my sine of 30 degrees would be your y, which is 1/2. Okay, isn't that beautiful? How it all just comes together? So it works nicely in your unit circle when you have your special right triangles occurring at 45, 30, and 60 degrees. Okay. All right, so jumping back to your notes, we just did our unit circle. So now we're going to look at trig functions of any angle. So we're going to let theta be an angle in standard position of x comma y at a point on the terminal side of theta, where r is equal to the square root. So here we're just solving for r in that equation of our circle in the box above. So r is equal to the square root of x squared plus y squared, where it cannot equal 0 because then we wouldn't have a circle. So for example 1, use the figure at the right to name the 6 basic trig functions in terms of x, y, and r. So now we're just keeping our r, not making it a 1 anymore. Okay, so if you look over here at the diagram, here's our right triangle, create it. Okay, we have this as x, this as y. So your sine is opposite of theta, which would be y, over your hypotenuse, which in this case is r. The cosine is adjacent, so x over hypotenuse, which is r. Tangent is opposite, so y over adjacent, which is x. Cosecant would be the reciprocal of the sine, so r over y. Remember, your cos don't go together. Secant is the reciprocal of cosine, so r over x. Cotangent, reciprocal of tangent, so x over y. Okay, so the unit circle is not that complicated. It's actually a really beautiful thing in how it works. You just need to make sure you understand it. Okay, so where are my trig functions going to be positive? Okay, so now let's think about this. We have our quadrants. Make a little quadrant over here. So remember, we have quadrant 1, 2, 3, 4. Okay, so sine, we said, was, I'm going to just make a triangle in 1 here for a second, just so we can see it. So we have x and y. Notice in quadrant 1, both my x and my y are positives, right? So if I were to do a sine, it would be a positive x over a positive r, which would be positive. Okay, which, since they're reciprocals of each other, sine and cosecant go hand in hand. Cosine is positive y over positive r, so it would be positive. Tangent would be positive y over x, or x over y, sorry. Oops, I didn't even do this right. Sorry. You're probably thinking, what the heck is she doing? This is x, this is y. There we go. So tangent and cotangent would also be positive. So all of your trig functions will be positive when your reference angle is in quadrant 1. Okay. Now what happens if we move our triangle into quadrant 2? Delete, 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 delete. There we go. So shift it over here. So now notice my x is now negative, my y stays positive, my r is positive. So if I wanted to find the sine, opposite of theta is positive y over positive r. Oops, how do I get rid of all that stuff? There we go. So positive y over positive r would be a positive. Notice how your cosine now would be negative x over r, so that would be negative. And your tangent would be y over negative x, so that would be negative. Okay. Now let's go down to quadrant 3. Let's put our triangle down here. So there's my right angle. So now we have a negative y and a negative x. R still stays positive. There's my theta. So sine would be negative y over positive r, so negative. Cosine would be negative x over positive r, so negative. But now what happens to your tangent? You have a negative y over negative x, which would go to a positive. Okay. And then quadrant 4. Let's do the same thing. X is positive, y is negative, r still always is positive. So my sine would be negative y over r, so negative. My cosine would be positive x over r, so positive. And then my tangent would be negative. Okay? So here all of them are positive. In quadrant 2, just the sine is positive. In quadrant 3, just the tangent is positive. And in quadrant 4, just the cosine is positive. So a lot of times students will come up with different acronyms, sayings to go with that. I grew up learning all students take calculus. I don't know, you probably can come up with something yourself. All students text constantly. All sloths take charge. That was terrible. So go with whatever you want. All students text constantly. All students take calculus. Maybe you have something that will help you to remember it better. But it's really important to remember where your trig functions are positive, because it's going to make life a lot easier to remember what your answers are going to be just based off of what quadrant your angle would lie in. Okay? Alright, so all students take calculus. So they're all positive here. Students, only your sine is positive here. Only tangent is positive in quadrant 3, and only your cosine is positive, and their reciprocals are positive in quadrant 4. Okay, so now let's look at this gorgeous unit circle here. We're going to fill it in. Oh goodness, that's way too big. I got to shrink it up. I think I got to shrink it up again. There we go. So your 16-point unit circle. You should be able to pull out your 16-point unit circle quite easily from your brain, because once you get quadrant 1 done, quadrant 2, quadrant 3, and quadrant 4 are just going to follow suit. It's just the signs that are going to be changing. Okay? So I'm going to do the easy parts first. So let's do our x-axis of 1, 0, and negative 1, 0. Let's do our y-axis of 0 and 1, and then down below, 0 and negative 1. Okay, so halfway between, so here we're at 0, right? So 0, and then we go up to, so we're in radians. This is pi over 2 right here, right? And then over here we're at pi. And then down on the bottom y-axis, we're at 3/2 pi. And then we get back to 2 pi. Okay, so halfway between 0 and 90 degrees, if we keep flipping back and forth in our thinking between degrees and radians, wouldn't this be 45 degrees? Yeah. So if I drop my reference angle here, my unit circle has a radius of 1. So what were our legs at? Root 2 over 2, root 2 over 2. So my x is root 2 over 2, and my y is root 2 over 2. Okay, now I'm going to erase that. So at all quarters, right, so where is my halfway mark over here? That would also be a 45-degree angle, right, right there. My x, notice, would be, so my radius is still 1, would be negative root 2 over 2. So I'm going to put a negative root 2 over 2. But my y would be a positive root 2 over 2. Now let's go down to quadrant 3. So quadrant 3 halfway is right here. They're both going to be negative, right? So negative root 2 over 2, negative root 2 over 2. Can't write small enough to get in that spot. And then over in quadrant 4, halfway is right here, right? Yeah. My x is going to be positive, so positive root 2 over 2, and my y is going to be negative root 2 over 2. Okay, so once you can remember your root 2 over 2 for your 45, then that's going to get you the same thing for this angle, which this angle right here would be 90 plus 45, so 135 degrees. Oops, that's terrible handwriting. And then it would be the same here, so 180 plus 45 is 225 degrees, right? Or negative 135 degrees. And then it would be the same at this angle here, which would be 270 plus 45, so 315. So 315 degrees, or negative 45 degrees. Or if we go into radians, negative pi over 4, right, degrees. And go from there. Okay, so we got our 45s done. So now let's get our 30, 60, 90s. So let's go to pi over 6. So if I drop my reference angle here, my shorter leg is going to be opposite the smallest angle, so it's going to be a 30 degree there. So again, remember this is 1. So my short leg is half of that, so 1/2. My long leg is going to be root 3 over 2. So my x is root 3 over 2. My y is 1/2. So now let's think about where the next one would be. Oops, I'm erasing everything. Erasing too much stuff. Zoom in. There we go. Alright, so where would be my next root 3 over 2? So where would my reference angle be? So remember, your reference angle has to happen with the x-axis. So it would be right here would be my next 30 degree. Okay? Notice that this would be my 1/2. This would be negative root 3 over 2. So my x is negative root 3 over 2, positive 1/2. Where's my next 30 degree going to be at? Well, it's going to be right here. Ooh, wrong. Right there. We got your next 30 degrees, right? So we have both negatives. So negative root 3 over 2, negative root 3 over 2. Or sorry, 1/2. I'm already losing it. 1/2. Don't make that mistake. Don't take credit that it's just so easy. You just make the mistakes. And then my next 30 degree would be right here, right? Oh, now I'm already changing colors. Right here. Good. Because that would get you another 30 degrees, right? 30 degrees. Okay, so that would be positive root 3 over 2, negative 1/2. Alright, so that leaves us with the 60 degrees, which goes up here to pi over 3. So 60 degrees, which tells me that my short leg is 1/2, and my long leg is root 3 over 2. So my x is 1/2, my y is root 3 over 2. Over here it would be negative 1/2, positive root 3 over 2. Down here it'd be both negatives, so negative 1/2, negative root 3 over 2. And over here it'd be positive 1/2, negative root 3 over 2. Whew, alright, there it is. So now let's fill in the actual radians for everything. So pi over 6, pi over 4, pi over 3, pi over 2. Adding 1/2 plus 1, what are we trying to get to? So 90 degrees plus, that would be 30, so 120. We got us 2/3, so this would be 2/3, that's bad. 2/3 pi. This will be 3/4 pi, right? This would be, so 2/3 plus 1/3. It'll be, not 2/3 plus 1/3, that gets us to 1. So it'll be 2/3 plus 1/6. Yeah, so 5 pi over 6. And then adding another 6 gets me to pi. Adding another 6 gets me 7 pi over 6. My next quarter would be 5 pi over 4. Adding another 6 to 7 pi over 6 would be 8 pi over 6, so 4 pi over 3. And then 3 pi over 2, adding a 6 there would be 5 pi over 3. Adding a quarter to 3/2 pi would be 7 pi over 4. Adding a 6 to 5/3 is 11 pi over 6, and that gets us back to 2 pi. Alright, I think we got everything filled in there, nothing erased. So, a full completed 16-point unit circle would look like this. Sorry for my terrible chicken scratch. You have all of your radians marked at each quarter, at each a sixth, right? Because 1/6, 2/6, 3/6, 4/6, 5/6, and so forth would get you all of the different units, right? Okay, so there's your unit circle. So once you have one quarter done, you should be able to easily get the coordinates for the other quadrants, right? And just take the signs of whatever quadrant that you lie in. All right, now let's keep on going. Example 2, now we're going to actually find exact values of the trig functions. So it says, summarize the exact values for 30 degrees, 60 degrees, and 90 degrees, rationalize denominators. All right, so here we go. Pi over 6. So remember at pi over 6, you remember if we look up at our unit circle, pi over 6, our coordinate was root 3/2, comma 1/2, right? Because pi over 6 is 30 degrees. So my sine is my y, right? Because remember this is the same thing as cosine theta, sine theta. So sine of theta, or sine of pi over 6, would be 1/2. Cosine would be my x, so the cosine of theta would be, or cosine of pi over 6 is root 3/2. Tangent is opposite over adjacent, right? So y over x. So this is the same as y over x, or y divided by x. So doing some work over here, 1/2 divided by root 3/2 is the same as 1/2 times 2 over root 3, which would be 1 over root 3, which rationalizes to root 3/3. Cosecant's the reciprocal of sine, so 2. Secant's the reciprocal of cosine, so that would be 2 root 3/3. I need to work that out, so it would be 2 over root 3 multiplying by root 3. Root 3 gets you 2 root 3/3. And then the cotangent is the reciprocal of your tangent, so that would be just root 3. That's what it would end up being, right? Because that would be 3 over root 3 times root 3 would be 3 root 3/3. Cancels. Yep. Okay, so we got all those in. Now let's go to 45 degrees. So remember for 45, our ordered pair was root 2/2, root 2/2, and we're in quadrant 1, so make sure you remember those signs for each of those. So the sine of 45 degrees would be your y, so root 2/2. Cosine would be your x, so root 2/2. Tangent would be those divided by each other, so 1. Cosine, or cosecant, is the reciprocal of the sine, so 2 over root 2. So 2 over root 2 would rationalize to 2 root 2/2, which is just root 2. Right, so root 2. Secant would be root 2 also. Cotangent would be the reciprocal of 1, so 1. And then let's do it for, do it for 60 degrees, or pi over 3. So that was at 1/2 root 3/2. So now my y for my sine is root 3/2. My cosine is x, so 1/2. Y over x, so root 3 divided by 1/2 is going to end up being just root 3, right, over 1. So root 3. Cosecant is the reciprocal of your sine, so 2 root 3/3. If you're not getting those in your head, do pause and do it out. Secant's the reciprocal of cosine, so 2. And the cotangent would be the reciprocal of root 1 over root 3, or the reciprocal of root 3, which would be 1 over root 3, so that would be root 3/3. All right. Good. Okay, so now let's go ahead and talk about quadrantal. Yes, quadrantal, funny word. The angles that fall on the actual axes. So a quadrantal angle is an angle whose terminal side lies along one of the coordinate axes. So evaluate the 6 trig functions at the 4 quadrant angles. Okay, so sine of theta at 0 degrees, which is going to put us right here at this ordered pair. Remember, sine is your y, so that's 0. Your cosine is the y. I hope this is confusing because it goes down now, is 1. Your tangent is, remember, tangent is y over x, so 0 over 1, which is 0. Cosecant is the reciprocal of your sine. So technically, my sine was 0 over 1. If I do the reciprocal and do 1 over 0, you can't have 0 in the denominator, so that is undefined. Secant is the reciprocal of the cosine, right, which the reciprocal of 1 is 1. Cotangent is the reciprocal of, so that would be x over y, which in this case would be 1 over 0, which is, again, undefined. You can't have 0 in the denominator. Okay, so 90 degrees puts us up at 0, 1. Oops, up here at half a pi. So my sine is my y, 1. Cosine is my x, 0. If we do 1 over 0, that's undefined. My cosecant's the reciprocal of 1, so 1. My secant would be the reciprocal of 0 over 1, so 1 over 0, so that's undefined. And my cotangent would be okay, because that would be 0 over 1, so that would be 0. Over to pi, or 180 degrees. My sine is my y, so 0. My cotangent is -1. My tangent would be 0 over -1, so, or no, yeah, 0 over -1, which is 0. I was about to say it's -1. My cosecant is a reciprocal of 0, which would be 0 over 1, so 1 over 0, undefined. Secant, -1. Cotangent, undefined. Reciprocal of 0 will be undefined. And then down at 270, or 3/2 pi, my sine is my y, so -1, 0, -1 over 0 is undefined. Reciprocal of -1 is -1, the reciprocal of 0 is going to be undefined. And then the reciprocal of undefined is 0. Okay, so those are called quadrantal angles, so angles that occur on your axes. All right, so the last thing we have to cover is our odd versus even trig functions. Okay, so remember that a function is even if when you plug in -x into the function, nothing changes. It stays the same original function. Okay, so for all x in the domain of f and the function, f is going to be odd when we plug in a negative, and your whole function ends up being the opposite in sign of everything. Okay, so even trig functions are your cosine and your secant, right? Because remember, cosine and secant are reciprocals of each other, so that would make sense that they are even functions together. So the cosine of -theta will come out to be the same as the cosine of theta, and the secant of -theta will come out to be the same as secant of theta. Your odd trig functions are the rest, so sine and its reciprocal cosecant, tangent and its reciprocal cotangent. Okay, so if we use this knowledge to evaluate trig functions, if I wanted to do the cosine of -60, well, that's going to just be the same as the cosine of +60 degrees. I don't know why, 60 degrees, right? And 60 degrees, remember, had us at 1/2 square root 3 over 2. And cosine is your x, so my answer is going to be 1/2. Sine is an odd function, so this is going to end up being negative of the sine of pi over 2. Remember, pi over 2 is up at 90, so 0, 1. Sine is your y, so the sine of pi over 2 is 1, but now I'm going to take the negative of it, so -1. Tangent is another odd, so that's going to be the negative tangent of pi. Pi was at -1, 0. Tangent is y over x. So 0 over negative 1, so 0, negative 0 is just 0. And then cotangent is going to be the same as the negative of cotangent of 11 pi over 2, right? So cotangent is the reciprocal of tangent, so cotangent of theta, and so instead of y over x, it's going to be x over y. All right, so now I've got to figure out where pi over 2 is. So pi over 2, if I take 11 halves and subtract 2 from that, I end up at 7 halves. Okay, so I'm still beyond it. So if I subtract another rotation of 2 pi's, so 7 halves minus 2 gets me to 3 halves. So this is really the same as 3 halves pi. Okay, so now I'm going to do the cotangent of 3 halves pi. Okay, and 3 halves pi is the same as 270. That's down there on the bottom of my y-axis, so at 0, negative 1. So my x is 0 over negative 1. So 0 over negative 1 is 0. And the negative of it would just be 0. Okay? All right, unit circle, 30, 60, 90, 45, 45, 90. Make sure we're good to go with that. Make sure we're good with quadrantal angles. And that concludes your notes. Bye, guys.